Okay, so thank you everyone for coming to the afternoon session. First up, we have Devin Hoover, who is an undergraduate in his junior year at the University of Chicago, who is going to be presenting a paper with actually me and Matt Payne, and Devin is currently applying for RU summer programs. So take it away, Devin.
All right, thank you for the introduction, Daryl. Like you said, hi, my name is Devin Hoover, undergraduate at the University of Chicago. I'll be presenting a brief overview of my work, which concerns the population of interstellar objects detectable by the LSST and reachable with two proposed in situ mission concepts. All right, there we go. So the existence of interstellar objects has been hypothesized as early as the 19th century, but it's not until recently that we've had definitive evidence of the existence of these objects. So far, we know of two interstellar objects. The first is Oumuamua, discovered in 2017, and the second is Borisov, discovered in 2019. The Oumuamua defied all expectations with its elongated shape, red and reflection spectrum, and non-gravitational acceleration, while Borisov seemed to be more of what we expected. So it remains for more of these objects to be detected to understand this population of unknown objects. So the Vera C. Rubin Observatory, a legacy survey of space and time, or LSST, will allow us to do exactly that. It will probe a vastly larger population of interstellar objects than previously considered feasible. And with its first flight expected very soon, estimates have been made for the amount of interstellar objects it should detect annually, ranging from 1 to 10. And those depend on the assumed spatial distribution, size frequency distribution, level of cometary activity, and other stuff like that. It also remains to look at the distributions of various parameters of these interstellar objects, like their impact parameters, sky locations, incoming velocities. So this is the main purpose of our work. So we simulated 1 million interstellar objects and integrated their orbits through the inner solar system using the n-body integrator rebound. So this schematic shows the hypothetical integration of one of our simulated objects. And then we impose detectability criteria to determine the sample that is detectable by the LSST. So the figure here shows the sky positions of the detectable population the moment they become detectable by the LSST. The brightest of these objects tend to concentrate near the ecliptic. I think it's worth pointing out that Oumuamua and Borisov seem to follow this trend. And in addition, there are significant concentrations around the solar apex and solar anti-apex. These seem to be remnants of the initial distribution, the galactic kinematic distribution from where I drew these synthetic objects. The histogram here shows the distributions of the minimum distances to Earth for the sample of detectable and reachable interstellar objects. And I'll explain what I mean by reachable later. So there seems to be a cutoff for at 1.5 AU for the detectable objects and 1 AU for the reachable objects, which seems to indicate that the LSST will preferentially select the interstellar objects that pass closest to Earth. The CDF shown here shows the delta V required for an intercept mission to reach each interstellar object. So we define reachable as having a delta V requirement of less than 20 kilometers per second. This corresponds to about 20% of our data. So this really gives credibility to the idea of an interstellar object intercept mission. So as Daryl mentioned in his previous talk, two proposed missions have been made, which had the interception of an ISO as one of or its main goals. So the first is the proposed NASA concept study bridge, which allows a delta V of 15 kilometers per second. And the second is the European Space Agency's Comet Interceptor, which will launch in 2029 and will be capable of a delta V of 2 kilometers per second. So the table here displays the percentages of interstellar objects in our sample that meet various criteria. About 3% of our simulated objects were viewed as detectable by the LSST, which corresponds between 9 and 19 objects during its 10-year survey. Okay, so the detectable in delta V is less than 15 kilometers per second, obviously corresponds to bridge. This translates to 1 object for the conservative estimate and 3 objects for the optimistic estimate. We assigned conservative and optimistic estimates based on the distributions of incoming velocities. So even with the conservative estimate, there is still 1 object that the LSST will detect that could be a candidate for bridge, which really makes the bridge mission feasible. Unfortunately, I can't really say the same for Comet Interceptor, whose percentages are just too low to allow for even 1 object to be detected in the optimistic estimate that merits an intercept mission. So it remains for the LSST to detect these objects, and hopefully we can get a better understanding of the underlying population of interstellar objects, and then fulfill the holy grail of the study of interstellar objects, send an intercept mission to them. I'd like to thank the organizers for organizing this, and now I will open it up for questions.
Okay, great job, Devin. Thanks.
Okay. How am I doing on time?
You are perfect on time.
Great.
So Joe has a question for you, which is how quickly can we get an intercept mission on the launch pad? And I guess, then to do a mission to one of these things like you're talking about.
Right. So obviously that depends on a variety of factors, be it what the NASA execs want, of course. But I can speak towards these sort of flight times. So we defined a parameter called wait time, which is sort of the heads up, if you will, between the detection of an interstellar object and the time an intercept mission can be sent there. So we found if you go to the QR code, that will be a link to our paper, and you can see the distribution of wait times. There is a cutoff at 150 days maximum for wait time. So I would say no more than 150 days to answer that question with, I guess, an asterisk in that answer. Hopefully that answers the question.
Okay, thanks, Devin. I think you have the distribution. I think you have the distribution of wait times you could also show.
Oh shoot, I didn't include it on the supplemental figures. I'm sorry.
Oh no, it's all good.
The one figure that of course I need, I don't have.
That always happens with the backup slide. So I think that is it with the questions, and thanks. Let's all thanks Devin again, and we'll move on. Thank you, Devin.
Yeah.
So next up, we have Junellie González Quiles, who is a second-year graduate student at Johns Hopkins and both an NSF graduate research fellow, and if I'm getting this right, also a GeoPath fellow. So take it away.
Hello, thank you for that lovely introduction. Hopefully you can see my slides okay. Yes, so thank you very much for coming and staying to hear my talk along with the others. I also want to thank the organizers for giving me the opportunity to present this talk today. And today I will be talking about the carbon cycling on the TRAPPIST-1 planets. Oh, okay, I can advance it, okay. So why the TRAPPIST-1 system? So the TRAPPIST-1 system was discovered in 2017 with 7 planets orbiting an M dwarf. And it is the interest of the SHAMPS collaboration to study the habitability of planets around M dwarfs. That and the fact that the TRAPPIST-1 system has guaranteed JWST time makes it a great target for habitability studies. And so which planets of these we're going to focus on? So primarily we're focused on the ones in the habitable zone. We're going to be focusing on planet E, as well as D and F. And we'll be talking about these planets more in detail. So then in terms of habitability, how is one way that we can talk about characterizing exoplanets? So one way is by looking at the carbonate silicate cycle. The carbonate silicate cycle is important to study because it is important for the climate of the planet. It regulates the levels of carbon dioxide in the atmosphere. And the way that the carbonate silicate cycle functions is that there's carbon dioxide outgassing through volcanism and mid-ocean ridges that goes up into the atmosphere. There's weathering involved. This takes that carbon into the oceans, which then is buried. And that carbon that is buried is eventually subducted into the interior of the planet again, and the carbon cycle starts all over again. And so that way we can look at the carbonate silicate cycle. It's a negative feedback cycle, which means that the more CO2 you have in the atmosphere, the hotter it gets, and that increases the rates of weathering, which then takes away that carbon dioxide from the atmosphere and lowers the temperature. And so that way, in longer timescales, it can regulate the temperature of the planet. And so what is my goal here? My goal is to trace the production of different gas species to determine the evolution of the atmospheric composition and its effect on planetary climate on the TRAPPIST-1 planets, specifically D, E, and F. So how do we get there? We get there by using outgassing models. And the way that we do this is by looking at geochemical cycles. We look at the deep water cycle, the carbonate silicate cycle, as I mentioned. We connect it to the interiors. We look at the outgassing from the interior and the gas species, hydrogen, water, carbon monoxide, carbon dioxide. And then we look at the atmospheres. And we study material properties like oxygen fugacity and melting properties. And I will explain in a moment what oxygen fugacity is. So oxygen fugacity is very important in studying and characterizing because it controls the relative gas abundances. And it also controls the carbon outgassing rates. And so the oxygen fugacity, we can see here in the right, we have a plot of temperature and the log of oxygen fugacity. We have the different iron species. And so the oxygen fugacity is determined by the line here. We can see, oh, I can use my cursor. It's okay. Number 3, that line is the iron-wustite buffer. And so a buffer basically means that it constrains the oxygen fugacity to follow along a certain value as a function of temperature. So that line number 3 is the oxygen is the buffer, iron-wustite buffer. And so we use the iron-wustite buffer specifically because it's the reducing end member like the moon. And we can also use iron-wustite plus 4, which means that it's that same line, but 4 units above it. And it is similar as a pretty oxidized state as the Earth. And so we can see here that it controls the relative gas abundances. So then to go into preliminary results, we have here the surface temperature with the different oxygen fugacities, iron-wustite, IW for short, and iron-wustite plus 4. And so the major takeaway here is that for most of its lifetime, in the iron-wustite case, it's lesser temperature, cooler temperatures than iron-wustite plus 4. And we used the Foley et al. 2015 surface temperature parametrization. And so the outgassing abundances, I want to stress that these are outgassing abundances and not atmospheric abundances, although we are working towards building to that using the outgassing abundances. We can see here the main takeaway is that planet D is mainly dominated by water vapor, and planet E and F are mainly dominated by carbon monoxide. And for the Arin-Woostead +4 case, we still see water vapor for planet D, and planet E and F are dominated by carbon dioxide. So then as a summary, models were run for both Arin-Woostead and Arin-Woostead +4 oxygen fugacity. We see the surface temperature stabilizing towards their equilibrium temperatures as a result of decrease in carbon outgassing over time. The next steps include improving our calculations of gas speciation and tracking atmospheric buildup of non-reactive species. And with that, I want to thank my advisor, Professor Laura Schaefer, and the whole CHAMPS collaboration, and also the NSF GRFP for funding me. And I will take any questions. Thank you.
Thanks so much. Do we have any, you can put your question, if we have any questions for Junellie, you can put them in the chat here or in the Slack. I'm monitoring both of those. And quickly, Junellie, I actually had a question for you, which was just, it seemed like, so you were kind of self-consistently doing, like in the very first slide, you had the CO2, the carbon silicate cycle, which seemed to reach a kind of quasi-steady equilibrium temperature. So I was wondering, how do you get the, but then your abundance of outgassing plots were changing pretty drastically over time. So how are you getting the outgassing abundance change? Is that all calculated self-consistently with some quasi-steady equilibrium? You see what I'm saying?
Yes. So I'm glad that you mentioned that. There was a lot of, so for the surface temperature, were you referring to the surface temperature calculation?
Yeah, I mean, this was the more complicated version, but I mean, also just the simpler schematic you had that was just CO2 and silicates, but then you add in other things there, but yes.
Yes, yes. So we incorporate, so the carbon cycle depends on the also like the deep water cycle. So we also like incorporate both of those. And then we also think about the speciation that comes with it, whether it's carbon monoxide or, you know, CO2 or water vapor or plain hydrogen. And so yes, we use that to build these models, if that answers your question.
Definitely. Thank you. And then there's a question in the chat, which is, what is the star symbol mean in the equation? What does the star symbol mean in the equation? And that's coming from Mark.
Oh, yes, that's for the Earth. So that's in reference with the Earth values. So the equilibrium temperature of the Earth and right. Partial pressure of CO2 in the Earth and temperature of the Earth. Yeah.
So would you expect to find, if you just randomly looked, would you expect to find it at the equilibrium, the final equilibrium temperature that you calculated? Is that a special state, or is that just what it will always relax to?
So we found that it stabilizes over time towards the equilibrium temperatures. Yes. Yeah.
Okay. Thanks so much, Junellie. I think we can move on. So thank Junellie for your input. Okay. You can post more questions in Slack.
Perfect. So, thank you so much.
Thank you. We were right on schedule. So thank you to all the speakers for sticking to the schedule. Next, we have Macy Huston, who is a graduate student and PhD candidate at Penn State. Take it away, Macy.
All right, does that look good?
That looks great.
All right, perfect. All right, so today I'm gonna talk a little bit about something kind of different. This is work I've been doing on technosignatures. Technosignatures are basically a category of biosignatures where instead of looking for evidence of organic life, we're looking for things like technology that life could create. This is also called SETI sometimes, but lately we've been trying to refer more to the technology aspect than trying to define intelligence. So I'm talking about evolutionary and observational consequences of Dyson sphere feedback. This is a project that I just finished up recently with my advisor and co-author, Jason Wright. So as you've probably all seen, at least in the sci-fi context, a Dyson sphere is basically a large structure around a star which harnesses its energy for some sort of technological use. It's a theoretical way to search for extraterrestrial technology that Freeman Dyson came up with. So in sci-fi, you'll usually see this as like a solid shell completely surrounding a star, but that's not really physically feasible. It wouldn't be stable. So kind of the more likely scenario is something more like what you might call a Dyson swarm, where you have a large number of satellites with solar panels on stable orbits around a star. So what we wanted to explore in this project is, can these megastructures, if they exist, affect the stars that they might surround? So kind of the first way to think about this would be if you're talking about Dyson spheres or Dyson swarms. They gather energy from a star, put it towards some technological use, like maybe computation, and then they will re-emit that energy thermally, most likely in the infrared. And now in this case, that light, that waste heat is going to be traveling out in all directions from the technology, and some of it might end up heading back toward the star. Now there's another kind of related scenario, another kind of technosignature theory that's called stellar engines, where you basically put a giant mirror near a star, intending to actually create motion to make the star move through the galaxy or something. And in this scenario, you would have a large megastructure that is directly reflecting a star's light, some of that coming back to hit the star. So we want to start thinking about this with, well, what happens to a star when it gets irradiated in general? So stars have negative gravitothermal heat capacity. That's just a fancy way of saying that if you add energy to them, they will expand and cool. And this is actually a result that you can just get from the Burial theorem very easily if you're interested. So what we're thinking about here is if that reflected or re-emitted light gets carried to the interior of the star, it can alter the star's structure and luminosity. And we would particularly expect this to happen in convective zones rather than radiative zones, where the energy at the surface of the star can be transported down toward the core. So we'll explore a few different types of main sequence stars with different distributions of convective and radiative zones. So what we're generally looking for as the consequences of irradiation is that the effective temperature of the star should decrease, its radius will increase, and as a result of those things, fusion will slow down and luminosity will decrease. And this will also result in the extension of the main sequence lifetime. And again, we really expect this to be strong in stars with convective envelopes that reach deep down into the star. So what I've done for this project is test this idea and really quantify it using the MESA stellar modeling software. So just a little part of this that I did, I'll explain very briefly before I got into the Dyson sphere aspect of it, was to examine how stellar structure and evolution are affected by constant temperature baths, recreating this work that was done actually in 1989 with more modern stellar modeling software. And the very short version is what I found is for stars around a solar mass where you've got a small convective envelope, but a mostly radiative star, the star is going to puff up and you'll see a significant change in the radius, but you won't really see fusion slowing down significantly or the main sequence lifetime changing. On the other hand, when you're looking at lower mass main sequence stars, which are convective on the surface and pretty deep down into the star, sometimes all the way to the center, you're going to see, again, a very high level of radius growth, as well as a significant extension of the main sequence lifetime as that fusion in the core really slows down. So next, we want to take a look at how this happens if your irradiation is a function of the star's luminosity. So let's say our technology is reflecting or re-emitting some fraction of a star's light back toward itself. So let's just start with basic stellar evolution. So when you're looking at a 0.2 solar mass star, I'm showing the evolution over time through the main sequence of nuclear luminosity and the star's radius. And you can see over time, the star will expand and heat up, increasing fusion. So this is just a plain star. Now let's add on a couple of our Dyson sphere models. So I've got 15% of feedback and 50% feedback levels. And you can see for high levels of feedback like this, you can get a really dramatic lowering of the luminosity, a growth in the radius, and extension of the main sequence lifetime of a star for this really low mass, fully convective star. Now, when we move on to a 1 solar mass star, you can see that the convective envelope of the star is dramatically expanding as we see a significant increase in the radius for high levels of feedback. But even for very high levels of feedback, we're not noticing much difference in terms of the nuclear luminosity because that radiative core is just not really being affected very strongly. And there's not really a significant change in the main sequence lifetime. And if we move on to a 2 solar mass star, which would have a radiative exterior, we see that none of that feedback is making its way into the star and affecting its bulk properties in a significant way. So this figure here, I'm just showing temperature, and then this alpha factor is the fraction of the star that's covered by our megastructure. My MESA models showed that the observable properties of a star are only going to change noticeably for very hot spheres. So you're looking at a little over 1,000 Kelvin for these low mass stars, which is a little higher than we typically think of for Dyson spheres, but not totally infeasible. On the other hand, for higher mass stars, they're not going to be significantly affected for any temperatures that we think solid material can exist at. So we can just kind of dismiss that as a possibility. So just kind of to quickly summarize, irradiated stars expand and cool, particularly in outer convective zones. Dyson spheres and stellar engines may irradiate a star through thermal re-emission or direct reflection, causing this effect. But the effect is only really noticeable for observation if you have pretty high levels of feedback, for example, pretty hot Dyson spheres. Another thing I did for this project that I unfortunately don't really have time to get into is generate some color magnitude diagrams for a wide array of Dyson sphere configurations, including much cooler ones, in order to motivate future searches of this sort. So this paper, actually, I got the email just this morning that it got published on App Day, and it's also available on arXiv. And I would be happy to talk any more about it now or on Slack or email. Thanks.
Thanks, Macy. That was a great talk. We have a couple questions and comments already. So Ravi was asking you, cool talk, Macy, where would the thermal emission blackbody curve of a Dyson sphere peak? Can we see the combined stellar spectrum and the thermal emission spectrum? And is it possible to identify the thermal emission spectrum? Then in parentheses, to identify a Dyson sphere.
Yeah, so generally when people are looking for Dyson spheres, they're looking for like a black body at like somewhere between like 300 to usually a little under 1,000 Kelvin. I don't have a figure right here of that, but let me send you a link to a paper where my advisor generated some spectra of this type.
Sure. What wavelength would that be peaking?
I don't have a number, but generally infrared.
Okay, yeah, thanks.
So then another question, Nicholas is asking you, would 50% feedback mean that 50% of the light incident to a Dyson swarm solar panel is absorbed and 50% is reflected back to the star? Does this mean the effect would only be noticeable for very inefficient Dyson spheres?
Right, so the 50% case is, that would be an example of a 50% case, but you can get noticeable effects for much lower percentages than that. If we're talking about low mass stars, I think the cutoff was about 5% feedback. So it's not that extreme. And then also another thing to consider is that if you can extend the main sequence lifetime of a star, you might actually want to do this intentionally reflecting some of that light.
Great. Okay, so I'm just gonna step in and ask you a question myself as take the chair prerogative here, but can you feasibly change via the process that you're talking about, change the interior structure of the star enough to significantly alter the dynamo and resulting flaring distribution?
That's not something I got into on this research. Unfortunately, I don't have an answer for you.
Oh, it's okay. Maybe we can talk offline about it. And there were a couple other comments and questions, so I think we can put those over to the Slack and thank Macy for a great talk. Thanks, Macy. Our next speaker is Keavin Moore, and Keavin is a graduate student at McGill. So take it away, Keavin, and you can share your, that looks good. We can see it all.
Awesome. Okay. Yeah, okay, so, hi everyone. I'm Keavin Moore. I'm a fourth year PhD student at McGill working with Nick Cowan. And my research is concerned with trying to determine the habitability of Earth-like planets orbiting M dwarfs based on the possibility that they have surface water through modeling. So for those of you that don't extensively study M dwarfs, they are much smaller and much less luminous than the sun, which is a G dwarf. And because of that, their habitable zone, so the orbital region where liquid surface water can exist, is much, much closer to the host star. And so because these orbits are very, very close, these planets are going to be bombarded with significant amounts of radiation across all wavelengths. But in particular, we're concerned with X-ray and ultraviolet radiation, which is collectively known as XUV radiation. And so this XUV radiation impinges on the atmospheres of these orbiting rocky planets, and it's very highly energetic, so it can photodissociate water molecules and cause them to escape to space. And if the escape is rapid enough, it can actually lead to complete surface desiccation of these planets. You'd have no surface water left. And so for the rest of this talk, I'll refer to an Earth-like planet orbiting an M dwarf as an M-Earth. So Earth is really unique. It has plate tectonics, and it's the only confirmed planet we know that has plate tectonics. And because of that, it's able to cycle water between the surface, where we know there's oceans, and the mantle, which likely contains multiple oceans worth of water. And so getting really simplified to that, the upwelling of water from the mantle to the surface, degassing, occurs at mid-ocean ridges, which is where new oceanic crust is created. Now this crust spreads away from the mid-ocean ridge towards the right there. And as it spreads towards the right, towards that subduction zone, the crust is hydrothermally altered and it incorporates water into its structure. And eventually it reaches the subduction zone on the right. And this hydrated slab is subducted. And while a lot of the water boils off and creates the subduction volcanoes you can see there, some of it will be regassed from the surface back into the mantle. And that'll complete that deep water cycle that is really unique to Earth because of its plate tectonics. And so we really tried to create a simple model of this to investigate the combination of having a deep water cycle and lost space occurring at the same time. And so we have a very simple two-box model. The surface reservoir is the ocean, and the subset of the surface is the atmosphere, where the loss is actually occurring from. And then we have the interior, the mantle, where you can actually store quite a bit of water. It has a very high capacity for water, and it's hidden away from the loss. So we ran models to try and figure this out. And as far as we were concerned, we assumed a planet was habitable as long as it had liquid surface water present. But planets actually begin very, very hot. So they wouldn't begin in a plate tectonic state. They would actually begin in a magma ocean state. And because they're also receiving very high levels of radiation, this magma ocean would be concurrent with a runaway greenhouse state. And so in our current study, we're working to incorporate this beginning magma ocean stage. And so we have a very, very simple parameterization of this magma ocean, and we allow it to solidify from the bottom up. And so as it solidifies, a very small amount, so about 1,000 times more water remains in the melt than is partitioned into the solid mantle as it solidifies. So the solidification front moves upwards, the magma ocean gradually gets smaller, but water is very, very highly soluble in this magma ocean. And so it will gradually become enriched in water. And when it is very, very thin, when you have a very thin layer of this magma, it will be supersaturated in water and able to degas that water into the atmosphere. You'll have 100% steam atmosphere just from that water. And so using this very simple parameterization of a magma ocean, we can test various timescales of the magma ocean solidification from the literature, just to get an idea of the interplay between the magma ocean and the runaway greenhouse stage. So we include two different regimes of this escape to space. And so the first corresponds to the magma ocean and the runaway greenhouse phase, which is usually concurrent. And so as the name suggests, the amount of water that you lose to space in normally this 100% steam atmosphere is limited by the amount of XUV radiation coming in. Now, on the other end of the spectrum, when you solidify the surface and you move into a plate tectonic regime, that's when you're out of a runaway greenhouse, the oceans mostly condense down onto the surface, and you have a little bit of water in the atmosphere still, but definitely not 100% steam atmosphere as earlier. And so now, when the runaway greenhouse is ended, the escape of water to space is limited by the vertical diffusion of water through the atmosphere. And so we can include both of these depending on the irradiation level of the surface of the planet. And so we can combine this over time and look at the evolution of the water in all of these reservoirs, starting from some amount in the magma ocean. And so the panel on the left shows the time evolution of the solidification of the magma ocean, the water in the 3 reservoirs I mentioned, the atmosphere, the magma ocean, and the solid mantle. And it's plotted on kind of a reverse log scale because all the action actually happens pretty close to the end of the solidification. When the magma ocean becomes supersaturated in water, it degasses nearly all of the initial water into the atmosphere, and a little bit has gradually been sequestered into the solid mantle. And so with this 50 million year solidification time, the runaway greenhouse is occurring at the beginning for the same amount of time. And so you have energy limited loss when this is occurring. The magma ocean solidifies, and for about 6 million more years, you're in this energy limited regime before the planet switches into having diffusion limited loss. You have oceans, the atmosphere condenses into an ocean. But the issue here is that there was so little sequestered into the mantle that the mantle rapidly degasses all of its water to the surface, and the mantle just remains desiccated. So there's no real cycling here, and naively, you would just expect water to be lost from the surface, and that's exactly what happens. So this is really just the null hypothesis. It's not the cool combination of cycling atmospheric loss that we wanted to see. So a good thing that we could probably do is stuff water into the mantle here. And our solution for this, hopefully, is to use a basal magma ocean. So I mentioned earlier that the water preferentially stays in the melt as the mantle solidifies. And so if you have this solid mantle with a little bit of water in it, but you have a residual basal magma ocean, there could be potentially lots and lots of water still stored underneath that solid mantle. And so if you conserve water, allowing this basal magma ocean to solidify as well, the water will be incorporated into the solid mantle, and so you'll have more than that very small amount we saw that led to mantle desiccation. But there's 2 concerns with this. The first is the depth of this basal magma ocean, which could be anywhere on the order of hundreds to thousands of kilometers. And I mentioned how soluble water is in these magma oceans. So there could be many, many oceans worth of water, hidden away in this basal magma ocean. And so it'll really determine the water storage, knowing how deep that is. And the other big concern we have is that the basal magma ocean could exist for timescales of billions of years. Now, this is much, much longer than the 50 million year solidification timescale I mentioned of our just simple magma ocean solidification. And if it takes billions of years for this to solidify, then we actually might run into the same problem I showed on the last slide, where there's so little water in the mantle for a given time that it just gets degassed to the surface and then lost to space, and not really interesting. So we're currently working on modeling this. Hopefully we'll have some of these results published in the next few months. And yeah, with that, I thank you for listening, and I would be happy to take questions.
Thanks, Keavin. We are close to out of time, but maybe time for a quick question if anyone wants to put one in the chat. Or Keavin, I'll ask you a quick question also, and we can also move this to the Slack. But for the 2 different models for the basalt inclusion of water or not, do you predict there to be very different levels of outgassing to and like loss of water to space potentially observable?
Oh, potentially observable. Yeah. I'm not really sure how to directly connect this to observables yet. Once we work out all the kinks of these models and can actually have them running, from the beginning of the magma ocean to the end, depending on whether or not you have that basal magma ocean or not, then I think maybe we could connect it to observables, but for now, we're kind of not focusing on that quite yet.
Okay, great. Thank you. One quick question. This is from Howard, did you include impact losses? I think that's something that might be very important, could cause significant elemental fractionation.
Yeah, that is a good point. No, we don't include impact losses yet. We're just trying to focus on the photo evaporation due to XUV as just a first start. But we can always improve the loss. And yeah, I believe impacts could be very significant, and that's something we hope to incorporate at some point.
Okay, great. Thank you. So next we have Dhvani Doshi, who is an undergraduate at Waterloo and currently looking for an internship or research position for the summer. So Dhvani, please take it away.
Okay, great. Thank you for that introduction, Daryl. Okay, there we go. So hi, my name is Dhvani, and I was working with Dr. Nicholas Cohen from McGill University this past summer. So the goal of my research was to use Earth as a proxy to understand how Earth-like clouds affect transit spectra, and if these clouds would be detectable by the James Webb Space Telescope. So through the research this summer, we came to the conclusion that Earth-like clouds actually will not be detectable by JWST if they existed on a planet in the TRAPPIST system. So we have the ability to characterize exoplanetary atmospheres and their molecular constituents with transit spectra. This can allow us to identify key biosignatures and gauge the planet's habitability. However, recent studies such as CHEMASTIC 2020 have noted that clouds can impact the transit spectra by significantly muting spectral features. These studies use GCM models, which can have intermodal variations, and at the end of the day are models, and so they may lack certain complexities involved in cloud formation and behavior. Therefore, we wanted to use real cloud data to see the impact of clouds on transmission spectra. And so we took data from solar occultations taken by the Canadian SciSat satellite. So the geometry of a solar occultation is similar to one of a transit. During a solar occultation, a satellite probes through the layers of the atmosphere and records the transmittance at specific impact parameters. Whereas during a transit, the instrument simultaneously probes the full range of a planet's impact parameters. As a result, to create a synthetic transit spectrum, we integrate the solar occultation data over the entire height of the atmosphere following McDonald and Cohen 2020. So we use solar occultation data with cloudy and non-cloudy sightlines. Low altitude clouds don't greatly affect the spectra as the opacity of lower atmospheric aerosols and Rayleigh losses dominate over clouds. As a result, this work focuses on stratospheric or high tropospheric clouds. So to first order, these would be the worst case scenario for an Earth-like atmosphere because of their higher altitude. So we look into the effect from tropical cirrus clouds, which form in the tropics. These clouds are of great interest because they can offer insight into things like global warming. And then we look at polar stratospheric clouds, which form in the polar regions, which are theorized to have a large contribution to ozone holes in the atmosphere. So with this data, we can see the effective thickness of Earth's atmosphere for a range of wavelengths for 3 different types of atmospheres. The black line was created using non-cloudy data around the globe, and so it represents a clear world average. The blue one represents a spectra with a global tropical cirrus cloud layer on Earth with the tropical climate. So as you can see, the clouds prevent us from probing deeper into the atmosphere. The surprising thing to see was that some of the peak features changed as well, which we didn't expect, as the cloud shouldn't affect transmittance at altitudes above the cloud deck. However, after developing a toy model that determines the optical depth during solar occultations, we were able to determine that it was a difference in temperature from the cloudy atmospheres that resulted in a change in the peak features. For example, polar stratospheric clouds form in extremely cold environments, and so this would increase the transmittance, allowing us to probe deeper into the atmosphere. So right now we have spectra for Earth, but we want to place this atmospheric data onto an exoplanet and evaluate if we would be able to detect these clouds on that exoplanet. So we added the effects of refraction onto the SciSat data, and then we also added noise modeling from Pandexo to create synthetic JWST observations. We look into 2 different systems, the TRAPPIST system and a hypothetical white dwarf system. So this shows the NIRSPEC and MIRI observations after 150 transits of TRAPPIST-1E. So here the data points correspond to the instrument measurements from JWST, and we can see their associated noise. I've also plotted the true spectra that we would be able to see if we had perfect instruments. So we can see that with the noise, we wouldn't really know if the cloudy observations match the cloudy spectrum or the clear spectrum. And so we can see that the error is still quite high. And so it's difficult to differentiate if the data matches either spectra. After creating a signal to noise ratio calculation, we determined that there is not a significant enough signal to distinguish clouds in this atmosphere. So we also wanted to look at a hypothetical white dwarf system because the larger radius ratio between the planet and star would provide a better SNR. So here you can see that you can distinguish between a cloudy and clear atmosphere after just 4 transits using NIRSpec. So we also used a spectral retrieval code, TauRex, to see if it can detect clouds and how the retrieved molecular abundances would differ with the 2 types of observations. So we find that TauRex was not able to significantly parameterize clouds with their cloudy observations. So forward models with and without the clouds basically match the observations with a similar degree of error. Moreover, the retrieved abundances didn't differ greatly when looking at the clear or cloudy observations. So in conclusion, using real cloudy data from solar occultations, we can say that if these clouds existed on TRAPPIST planets, they wouldn't affect the transit spectra by much and would likely go undetected. However, these clouds could potentially be detected on an Earth-like planet orbiting a white dwarf. So this has its own positives and negatives. The downside is that because we can't observe these clouds, there's a slight layer of complexity that we may not be able to understand for that exoplanet's atmosphere. However, because they are virtually undetectable, they also won't impede on the detectability of biosignatures, which we hope to characterize for these planets. So yeah, thank you for listening to my talk. And I'd like to thank the organizers for giving me the opportunity to present. And I'd like to open the floor to any questions.
Thanks, Dhvani. So Keavin, there are a couple questions already. So Keavin was asking, did you consider JWST wavelength shorter than 3 microns?
So we were restricted with the wavelength that we could use because of the SciSat ACE-FDS instruments. Like they themselves have a specific wavelength range in which they record the data. And so we couldn't really stray from those wavelength ranges. And that's reflected in the instruments that we chose to use for NIRSpec and MIRI.
Great. So Ravi has a question, and I think maybe wanted to just turn on the microphone and ask it.
Yeah, so I thought it was quicker to ask here. So the clouds are based on the Earth-like tropospheric clouds. These are the ones that you use, stratospheric clouds, sorry, you used, right? So there are some studies that have shown that 3D clouds, if you do a 3D modeling, the clouds have a different structure than what we see on the Earth-like clouds on these planets around M dwarfs. So if you have you considered them, and do you have any plans of doing that in the future?
Yeah, so I think that's a really important thing to raise. So obviously our research, like the scope was very narrow in terms of Earth-like atmosphere. I know a previous paper by Fuji, I can't remember the date, but it was NRI-driven atmospheres. They also had a GCM model around an M dwarf, I believe, that had an Earth-like atmosphere. And they had stratospheric clouds that were optically thin. And so they were similar to ours, and we saw similar results, like we could easily compare our results to theirs, and they were similar. But again, yeah, a lot of GCM models with M dwarfs have shown that they have a lot of different types of clouds than what you would see on Earth. And so I think it would be interesting to look further into that. But again, we wanted to focus on like real cloudy data. And so we couldn't really stray from looking at something besides an Earth-like atmosphere.
Good. Thomas Fauché, Arin May, and Tad have a couple of papers on that if you want to look at it.
Okay, thank you so much. Yeah, I'll definitely look into that.
So Ryan was asking, for the white dwarf systems, which white dwarf was the planet model based on? And what was the map?
Yeah, so I modeled the white dwarf system based off of HD 1856, I believe. Basically, I took the parameters that were given in Kazakis et al. 2020 and Kaltnager et al. 2020.
Okay, great. And Tad was asking, at what pressures or altitudes are Earth-like clouds optically thick in transmission in the occultations?
So we find more optically thick clouds once we reach the troposphere, because that's basically where there's the majority of Earth's like aerosols and water vapor content. Once you reach the stratosphere, it becomes pretty dry. But again, as I mentioned before, because of like refraction limits, it's hard for us to even probe up to the troposphere. So those clouds might not really matter at all. But yeah.
Okay, great. Thanks. You're out of time, but there are more questions. So
Okay, I'll be sure to answer them on Slack.
thank you. So finally, we have Arin Avsar, who is a fourth-year undergraduate at UC Berkeley and also applying to graduate school currently. So take it away. This is the last talk of the day. So thank you all for keeping to your time.
Thank you, everyone. So yeah, I'm Arin. I'm a fourth-year undergrad at UC Berkeley, and today I'll be presenting our work on the large-scale structure of debris disks newly imaged with HSD STIS. So as a quick reminder, debris disks are the rocky and icy leftovers of planet formation. So our motivations for doing this work is to characterize morphological and surface brightness asymmetries in debris disks over large scales. So this figure to the right is a well-known example of an asymmetric debris disk, more specifically HR 4796. And on top of this, asymmetries are a sign of potential disk interaction and external perturbations. And these perturbations can include interstellar medium interactions as well as stellar flybys. And this on the bottom right is a theoretical asymmetric debris disks that were put forward by Li and Chang in 2016. So our main goals from this project were to detect the extended morphologies of the disk, previously detected with GPI and sphere at narrow fields of view. From these disks, we want to chronographically image 9 debris disks in optical scattered light with Hubble Space Telescope's Space Telescope Imaging Spectrograph, otherwise known as HSD STIS, using bar and wedge occulters. And on top of this, we'll be doing a reanalysis of HD 106906. So a quick background on these disks: they have ages between 10 to 25 million years, and 8 of the disks are in the Scorpio-Centaurus Stellar Association, plus 1 young field M dwarf. So just as a reminder, GPI and Sphere are high contrast ground-based instruments on Gemini South and the Very Large Telescope, or VLT, respectively. And this is the gallery of the inner parts of the debris disk previously detected with GPI and Sphere in the near infrared. These results are what motivated our work to image the larger morphology, or the larger morphologies of these disks. So this is the gallery of the detected disks with HSD STIS. The images here are the averages of both bar and wedge data sets. And then of these detections, HD 115600 is a tentative detection, while HD 145560 was a lower inclination disk, while the rest of these are edge-on or near edge-on disks. And then of the two disks in the previous gallery, 2 of them are non-detection, so they are not with STIS, so they're not imaged, or they're not shown here. So just to give a sense of like physical size, HD 146897 is the largest disk that we were able to detect with separations of approximately 800 AU from the host star. And finally, the data reduction method used was RDI, or reference differential imaging. And the light we see, some of the light we see around the disk is residual stellar PSF after the reference star's PSF was subtracted. So I'm going to get into the main component of our analysis, which was measuring the radial surface brightness profiles. So here is an image of, the 2 images are both of HD 129590. The right is a visualization of how the radial surface brightness profiles were measured. Basically, we placed apertures of size 2 pixels, or approximately 0.1 arc seconds, along the disk midplane, which is represented by the red and orange points you see. And the pixels in the aperture were then averaged. And then additionally, these background measurements were done perpendicular to the disk, and the 1 sigma uncertainties were combining both background and photon noise terms. So here's an example of two examples of the radial surface brightness profiles of HD 129590 and 106906. The dashed lines you see indicate the radius from the host star where the signal to noise ratio hit 1, or basically where the disk became indistinguishable from the background. And you can see that HD 106906 exhibits a brightness asymmetry while 129590 doesn't. And this asymmetry is also shown by the actual placement of the dashed lines, or where the SNR becomes 1. On the eastern side of 106906, it hits 1 at around 400 AU, while on the western side, it doesn't become 1 until 600 AU, and that gap is not seen in 129590. So this surface brightness asymmetry of 106906 can also be compounded if in this top right image, where you can see the actual morphology of the disk. And then finally, out of the edge-on disks detected with HSD stis, our preliminary results show that 5 of the 6 disks are morphologically symmetric at large separations, while 1, that being HD 106906, exhibited morphological asymmetries. And then the final portion of our analysis was actually fitting a power law to these radial surface brightness profiles. And so the reason for doing so is understanding how the dust is distributed in a disk gives a hints about the type of physical mechanisms occurring. And according to theory, power law indices of -3.5 are signs of collisionally dominated debris disks, meaning not too much perturbation is going on. So if we were to find a power law indices that were not -3.5, this could potentially point to disk planet interaction or external perturbations that I mentioned in the motivation slide. And finally, just how the model fitting was done. We used MCMC, or Markov chain Monte Carlo modeling, and we're specifically focused on the morphology of the disk at large separations. So some of the disks, so some surface brightness profiles might exhibit broken power laws. So we're specifically focused on the outer portion of the disk, so the power law that adheres to the outer portion, if the inner portion might exhibit a separate power law. And so our preliminary results from this show that the power law indices of the disks range from -3.5 to -2.4. So to conclude, 8 disks were detected, including 1 archival data sets, and we had 2 non-detections. And the radial surface brightness profiles of the edge-on disks, 5 of them showed morphologically symmetric, or were morphologically symmetric at large separations, while 1 exhibited morphological asymmetries, again being 106906. And so future work on this could be understanding the origins of this range in power law, these ranges in power laws that I mentioned in the previous slide, which will be discussed more in our paper currently in prep. Yeah, I want to thank everyone, the organizer of this event, and I'd be happy to answer any questions.
Great. Thanks, Arin. That was a great talk and great way to close down the day for a great conference. You've got some questions already in the Slack. Alicia asked, have you looked at the surface brightnesses of the disk midplanes for the edge-on disks to quantify large-scale out-of-plane dust?
Yes, so if I go back to right here. So there is one thing that will be discussed in the paper that I didn't really touch on here, is that there is some detectable disk at this part, in this part of 106906, that is not seen in the other edge-on disks. And so we're currently investigating the statistical significance of that brightness, whether that was from the data reduction or if that's an actual physical feature. So that is being discussed, or that is one part of the surface brightness profile that's being measured off of the disk midplane.
Great, thanks. I wanted to ask you about the, which I wanted to ask you this question, and then you talked about it, that you were going to talk about it in the paper, but do you have any idea about what the differences in the power law indices could mean?
So not at the moment, that we haven't explored too much yet, but that will be, once we do explore that, I'd be happy to send you the results of the different power law indices.
And then, I mean, for the different masses of the different disks, like, do you have any idea, like, if there's a range of like Q values or like how important the self-gravitation of the disk could be itself?
I do not at the moment.
Okay, maybe we could
but
talk
again,
offline about it. But
Yes. Yeah.
could be pretty, there could be, that looks definitely intriguing about the differences in the power laws. And I think we are basically out of time anyway, but I think there are more questions that can be transferred to the Slack. So thank you for a great talk, Arin.
Yeah.
I'll hand it over to Arin.
Great. I want to thank everybody, first of all, for sticking around until this late in the day for those of us on the East Coast. We wanted to fit as many talks in as we could. So Laura has thrown up a quick little slide about things to do before you join us tomorrow. So if you haven't joined the Slack, please do so. If you don't have the link to join the Slack, if you go to our CHAMPS website and register for the event, I will send you that link as soon as I see your email registering. Once you're in the Slack, please introduce yourself in the introductions channel and chat with all the other people that are attending the conference or seminar or talk series, whatever you want to call it. As we mentioned before, we have the Exoplanet Early Career Highlight channel where you can advertise your job advertisement or your own job search and network with some other people that might be able to help you with those. We have the channel that we were talking about, talks and answering and asking more questions today, Thursday, January 13th. That's going to stay open. That's not going to go anywhere. But tomorrow we'll be moving the conversation to the channel Friday, January 14th. So if you're not in that, go ahead and join that channel, please. We also have this channel called Bonus Abstracts. Unfortunately, we weren't able to fit everybody's talks and posters here. So there have been a few people posting additional abstracts on the research they've been doing in there. So take a look and ask questions about what everyone else has been doing. The random channel has turned into a great fight between cats and dogs. So if you want to contribute to the best pets, please post pictures of your pets there. And otherwise, we will see you tomorrow at 11 a.m. Eastern, 8 a.m. Pacific for another full day of talks.